Hello everyone, welcome to another stream. How are we doing? So, let's adjust these levels here. So last stream was pretty awesome. We got let's open up Vim on this one. Here we go. So we got something rendering from this sort of LOD and cluster system. Let me change something where we build every frame. Right, so it's going to build every frame now. It might jump around even more. Yeah, it's really glitchy. Okay, we'll disable that. When we actually want to see something. So yeah, last stream we got something working, but as you can tell... Oh, where the hell has it gone? As you can tell, it's a bit glitchy. And we've lost it now, apparently. Huh. What is it? Oh, all zero. Shoot. It's not building it at all, is it? Duh. Right. There we go. Right. So it builds this sort of 3D volume of spheres, and it kind of does it in a very poor way. Something is definitely buggy and wrong with this thing. But yeah, but now we've got the thing up and running, we're able to sort of see how long things take, and how many things that we can render with this system. And but yeah, as soon as you get very close to it, the ray tracer takes a very long time. Well, no, this is not so bad. This is about 1.5 ms, but we haven't even got the full thing up and running yet. Where's the binning code? Oh. Yeah, the binning code's taken about 5 ms, which is a bit too long. Oh boy. Anyways, so it's still a bit buggy. And if we run the building code every frame, which we're going to want to run this thing every frame. Hey there, I can't see with my phone. Alice. Welcome to the stream, how you doing? Welcome. So we run the builder code every frame. You'll notice that there's quite a lot of steps. Let's close this. And, you know, just to sort of build the initial tree, it's about 5 ms, right? 5 milliseconds. And then to do the refinement after that, it's about nearly 2 ms. Which is not too great. So we definitely need to have an optimization pass over this and make it better as well. But yeah, so it got me thinking about different ways that we could optimize this, because the thing is we can go and fix the bugs, and then have it up and running just to realize that it's not, you know, fast enough. Or I could think about how we could redesign this thing to make it faster, and then just have a second attempt at it, basically. So I think the crux of the issue with the design, let's get Milton up, is the fact that our cluster size is too small. So I thought this would be a problem, but I just wanted to try it out. And it kind of leads into other questions as well. So right now we've got this sort of limit of a 256 cubed volume that you fill up. And it's all and the clusters are 2 by 2 by 2, so you have 8 spheres per cluster, and there's like a tree of those going down from the lowest level of detail all the way down to the highest, and there's this limit. Now the reason why I had this limit here is because the algorithm I thought of constructing this needed to have a hard limit. But I think I've thought of a way where we might be able to remove that hard limit, which would be amazing, because then when you sort of create your volumes, you don't really have a limit, like a boundary, and then you have to sort of break out into another volume. Or we don't have to program something where we basically glue volumes next to each other, then have sort of problems when we zoom out or something and have to LOD those things. It'd be weird. So yeah, that's not a good solution. So effectively, let's get the calculator out. So we're doing like 2 cubed, right? Let's go and get some proper calculator out. That one. So right now we do 2 cubes, obviously it's 8 spheres. So along an axis, yeah, so basically 2 to the power of 7, right? Is this right? No, 2 to the power of 8, that's what I meant. 2 to the power of 8 get you 256, right? And that's our restriction here at the moment. So yeah, where was I going with this? But yeah, I'm thinking about removing the restriction basically. And if 7 having 2 cubed clusters, we're going to probably move to 4 cubed or 8 cubed. I've just got to figure that one out. So 4 cubes will get you 64, and then 8 cubes will be 512. So this will fit better when we process the clusters. Because in shaders right now, I do something a bit silly, where when we process in every sphere within a cluster, right? So there's only 8. And GPUs work better with basically wave 32, 32 threads run in lockstep. And ideally, if you could have a thread group which is bigger than 32, I'm pretty sure it does pay off as well. But you don't want anything that's like massively bigger. Just a little bit bigger, maybe anywhere in between the range, I guess, of 64 maybe to about 256. But maybe 512's alright. This way we've got to play around. So where's a good example where it's bad? So here we've got the fact that we only have 8 children or 8 spheres per cluster means to fill a wave 32 we have to times it by 4, and that means we have 4. So the y-axis is used for nodes. So there's 4 nodes, 4 cluster nodes being processed in a single wave, right? A single compute unit. So every instruction that gets picked up has to, like, it's doing 4 nodes at a time, and 8 spheres in each of those nodes as well. So you have problems where, like, branches are not always taken, you get inactive lanes, right? Where obviously 8 lanes will go in here, or 8 threads will go in here, so long as the node passes this thing. But if a node doesn't, you've instantly lost 8 threads, right? So there's problems like that you have to deal with, but also indirect memory accesses as well, I imagine. Like, it might be alright getting access to, like, as an example here, when you have 4 threads, sorry, when you have, you got this kind of issue here, right? You're trying to execute a line of code. And to execute that line of code, you need to have access to 4 nodes, which could be in different parts of address space, right? Before you even execute this line of code, you've got to go ahead and fetch all the cache. You got to fetch these into cache, right? And then you can load from them. And then furthermore, each of these nodes have an array of spheres. So guess what? That's more indirect data. Where there's another array of spheres over here, there's an array of spheres over there, there's an array of spheres over here, and so on, right? To the point where you've now just like had to get all these different memory locations, like 4 times as more memory locations before you can execute a single line of code here. So I think, right, it's just my guess, there's those 2 things which will bring a big win in performance. Basically, you should have more utilization of, or the thread should just be able to carry on more and wait around for less memory. So, and have less branches that go. So I think that should be a big win in performance as well. And another big win about increasing the cluster size as well is we have far too many clusters, and the amount of so say if you're going to be doing any like occlusion culling, which is something we still need to implement, and I have an idea of how I want to do that now since I've been doing this research. But the idea is the number that was walking away with, right, is after implementing this. Let's get out the documentation. Here we go. Maybe we can play with this today. So the thing that had a problem with, well, okay, the thing that we potentially have an issue with now is this render that we was seeing on screen. Here we go. This render that was seen on screen, which is really buggy. The amount of clusters that it uses is I think it was about 489,000, right? Clusters. And you multiply that by 8. That's how many spheres roughly we have, because they're 2 by 2 by 2s. Now, that's just for one volume. So if you have, if you have 1,000 volumes, that's a lot of clusters to occlusion cult, right? So by increasing, so again, if we just take this, if we just do some numbers here, we were doing like 128 cubed of wait, I've got 2 calculators open, haven't I? Wait, close this big boy. There he is. Right, so if we were doing, I think it was 128 cubed clusters, because at 256 are 2 by 2 by 2, right? So it's just half, right? So there's that many clusters in a 256 cubed volume of spheres. But then, so if we increase the size of the clusters, this number can go down a lot. Ah, Shylex, how you doing? Thank you so much, man. Appreciate it. How you been? Cheers. Thank you so much for the sub. Really appreciate it. How you been? So if we do just up it to 4 cubed, right? That's 64. That's 64. Actually, there's 2 64s here, so it just confused me for a minute. That's 64 spheres in a cluster, and it's because it's 4 by 4 by 4. It's 256 divided by 4, and that's 64 clusters to fill a 256 volume in this example. But we're removing the 256 problem anyway. So this means if you cube this, that's about 250,000 clusters instead of the 2 million that we saw. So it's basically divide by 8. So we took that sort of number that we had here, divided it by 8 as a rough guess. That's how many clusters we'll be having instead of that 500,000 number. And when you have like 1,000 of these guys, it's maybe 63 million clusters. So that's just if you do 8. Sorry, if you do 4 cubed. But if you do 8 cubes, there'll be even less. There'll be 8 less, right? So there'll only be 8 million there instead. Yeah, so much smaller amount of clusters to call, right? So yeah, these are the sort of things I've been thinking about over the past couple of days after we've got this implementation up and running. So what I want to do in today's stream is do a design again from the ground up and remove the limitation of the 256 cubes volume. And I wanna up the size to maybe 4 or 8 cubes, and we'll have that as a variable size, so we can actually choose and see which one is actually better. So we could have it as a constant somewhere, make sure that constant is something, right? So we'll still be doing an octree of clusters, and we're going to remove the limit now. So this means that people can make... Hey, Renzel. How you doing? Thank you so much for the sub. Appreciate it, sir. Just lurking the most, still yet to catch up my own knowledge and all the cool stuff you're up to with this game. Always impressive watching you work. Thank you so much. Yeah, it's good. In a bit of a you know, just spent like maybe 14 streams doing something that we're going to rework now, but it's been necessary to sort of learn and understand things. And I actually want to show a video now, because I want to show sort of where some of this, like how we're going to do some of the occlusion culling, which should ultimately mean that we can render a whole ton of spheres. And I'm actually quite optimistic now with this rewrite and this design we'll be doing. So yeah, we're going to rewrite this document and just completely remove limitations and make it so artists don't have any problems basically just creating what they want. And we shouldn't have a problem where we have like a volume that's a restricted size, and you sort of zoom out, and the highest LOD would be that. And this is only 256 spheres. Sorry, the lowest LOD would only be this. And if you wanted to do like a meter's worth of spheres or whatever, you can have another sort of LOD out of there, basically. Obviously, the artists will still have limitations where they can go too much into detail, I imagine. But that's fine, because we can just do that. We can control that when we make the assets. I'm tired AF. What have you been doing, Ransel? I get you, man. I was like that the other day. That's like me 50-50. 1 minute tired, 1 minute not tired. So let's go to YouTube. We'll do it in the incognito window. And so I think it was 2021, day 1. Here we go. So there's a great talk here by, there you go. So let's skip past this. This is basically talking about occlusion culling and rendering meshes using clusters. And this is basically what we're trying to achieve, right? We're trying to cluster spheres, right? Or, together, and have essentially like a tree of them. But we had this weird restriction on, which I've I've thought through, and we should be able to lift it. So basically, it falls down to like a mesh clustering system, and this is talking about an occlusion technique that you can do as well. So this is why I'm pretty optimistic that we should be able to achieve something similar. So I think we'll just play this video, and then we'll get into the design. Let's mute some music. I'll drop a link to the whole video in the chat for those who are interested in watching it for themselves another time or whatever. I dropped the right link, right? Yeah, I did. Yeah, I just got up the volume, you see. So that's 26 decibels. Right there. Uh-huh. Is the volume good everyone? Someone just let me know. Thank you. Great. Thank you, Sophie. So again, this is kind of what we kind of had, right? But we had like our classes were 2 by 2 by 2, which was kind of a bad idea, and we had a limit of like this volume around said bunny, or maybe subpart of bunny, being 256 cubed. And then you can sort of like, you couldn't sort of have a tree of volumes, and it's very bad. But again, managed to think through that restriction now. I'm pretty sure we can remove it and just have clusters all the way down, basically. So you just pay the cost of having another level of clusters. So let's carry on. So before we get to that, I just want to quickly talk about this sort of different LOD thing. And if you remember, we have had a feature in our thing that was programming up where you'll be able to paint spheres down at different LODs. So this is kind of what it is, right? And also our spheres, they fit on a grid. Now, they might be sort of offset slightly on the grid so we can maybe avoid having holes where the spheres sort of joined together. But that's a future thing. But the idea is when you sort of paint down these spheres, they're you can select an LOD that you're painting at, and that's how we control having different sized spheres, but they also fit on a grid, so they're easier to sort of work out initially. And then when we sort of go to render them, we're going to go through this sort of tree and then take them from this gridded space and then just turn them into some ellipse in world space that's based on like transformations, like bone transformations and all sorts of stuff like that. Maybe some velocity or whatever. I don't know, to get some sort of organic looking sort of breathing thing. But anyway, let's just carry on with the next step. So this is the next step is basically want to make this system actually work. So just to sort of give more detail on how this works, if for those who didn't sort of follow, basically you would have your instances, right? And they've got like a cluster in there, which is probably, so for us it'll have like, imagine 4x4 or 8x8 spheres in here at the lowest LOD. And then you're sort of just going to dispatch over this cluster and just see like, well, you go over the instances first and you say which instances are they big enough to be rendered? And if they are, then you would just add the sort of the root cluster, you know, to a list, and then you do another dispatch, and you basically go over all the clusters now and try and occlusion call those, and you'll go down. You look at all the children and see if they exist. If you have child clusters where each of the spheres would be, right? As sorry, wait, child clusters might be in a it's actually it's a 2x2x2, so it's like an octree, right? And you check each of those, and you see are they big enough to be sort of rendered on the screen, and if they are, you'll tunnel in again. But also, every time you're sort of checking if they're big enough to be on the screen, you're checking the occlusion buffer to see if they're occluded by another object, and then basically you can cull really early. And the whole thing that makes it work so you can render stuff at very small detail is you catch a large amount of the stuff you could render really early, and you'd never have to you never have to traverse down the tree and check anymore, right? Um, So for those who didn't fully understand, basically you get you've rendered a frame, right, from last frame, and you got the buffer which tells you the depth at every pixel of where like the Phyllis opaque thing was, maybe. Or but anyway. Um so you keep that for the next frame. And then when you're sort of going down your tree of clusters from the top, you check to see if that cluster is occluded by last frame's one. If it's occluded, and you could be really high up in the tree, and you say, hey, this one right at the top of the tree is occluded, or maybe you've traversed down a little bit, but you're still kind of high up. You say, oh, this one's actually occluded, so you put that in an array somewhere. But for the ones that do make it through, and they're not occluded by last frame's occlusion buffer, you can literally just like you can literally just pass that one to the renderer and put pixels on the screen. Now, after you've done that, you take the depth buffer from the stuff you've just rendered, right? All the stuff that passed the test, and then that's your new occlusion buffer. And then you basically just go over the list of stuff that didn't render back here, and you carry on and try and either they're big enough to render, or you go down and find the smaller clusters that you want to render and keep testing those ones against the occlusion until you basically either they're all occluded, or the one you found a list to render, and then you like render the final lot which you missed. And with that sort of technique, we should be able to render just like tons of spheres, because we're just basically getting rid of a whole ton of work, right? And we're doing it from like very coarse to very sort of like fine, right? So you're starting coarse and getting rid of tons of stuff, and then you're going down to the fine detail as you traverse down the tree. So yeah, that's kind of the occlusion strategy we want to use. But it's great that we've been able to think about how to remove that 256 cubed volume restriction. Let me just adjust the levels back, and then we'll get going with the plan. And this plan is going to be awesome. Gonna be awesome. No, I didn't work on Little Big Planet. I worked a bit on Dreams though. I came towards the end of the development. I put the decals in there. That's one of my things. That's the thing that got released when I worked on Dreams. Is the decals. So you put decals down on the sculpts and stuff, which is pretty cool. All right, so redesign time. So I think we're going to be able to get an awesome version second time around, and not necessarily have to do a third or fourth or fifth or sixth. So I think we've got this. Like, I've learned a lot by doing this first one, and I've got all the missing pieces now, I reckon. So, and we're going to make it configurable to test two different things. I'm not between two different options. I'm not really 100% sure on which one is better. So that is a cluster size of 8 or 8 or 4 cubed, something like that. Meanwhile, I can't even query a database. Man, I can't even query a database. Whenever I try and do any database stuff, I get like, weird syntax errors, and then the database errors are like terrible. So I just don't use databases. One day they might be useful for me, but I've not needed them for So yeah, what is the aim? The aim is to stress test. The aim is still the same, right? Build a stress test scene, with a bunch of models so we can test performance and graphical features, right? So we want to be able to build some big like scene with tons of different like models and instances of models and have this scene so we can sort of build all the graphical features and sort on top of that, right? So that's the aim. So we need to be able to build a scene first. So these are the sort of things I wanted, right? Multiple instances, different models, LOD clusters, variable ball size, occlusion buffer v2, dynamic animated model instances, and a model editor. That's what I wanted to build towards. I was, so this is the old thing. Let's like do that so it's out of mind, and let's start writing like what I have, and we'll sort of peek down at the thing below and sort of maybe bring some of that in. So the basic idea is we're going to have probably we're going to have a volume still. Let's do like the idea of a volume, or we could call it a model. Yeah, so the volume is like a tree of clusters, isn't it? Yeah, let's say that. So let's say a volume. This thing is a tree of clusters. Right, a cluster is a cluster. So this is an octree. Is an octree node, right? And obviously nodes can have children, right? So, but then it has with sort of 4 by 4 by 4 or 8 by 8 by 8 spheres. So I want to be able to like animate these things as well. Oh, there's one more thing I wanted to mention. The other good thing about that occlusion thing we've just watched is it's not limited to static objects, right? Because what I plan on doing is having these like volumes of spheres. And when you sort of animate them and move them, they might stretch apart a bit and cause like spheres to sort of show the spheres behind and stuff like that. And maybe even eventually you do it enough, you can see all the way through it. But the beauty of the occlusion thing that we just watched, using that method, it can work on both static objects and animated objects as well. They can both be used as occluders, basically. It does have one problem where the first frame is going to be slow because it basically has to render everything. For the most part, it has to render everything. So we might have to add a little case where we find maybe the biggest occluders and just render those first. But we'll see when we cross that bridge. Or there might be another way around it. Right, so we're just going with like so we're removing that 256 limit. In the old things here, we had a limit of 256 cubes. Originally it was 1024 cubed. But then we realized it was too much memory to store. But anyway, we've fixed that now. Because the way I've thought we can build it without doing any of that. So what else? So basically like a volume, probably have like a thing of these, right? So are we still gonna do like a BVH? Yeah, so when we do GI, we might need a BVH of the of it instead, basically. Maybe. We'll see. Right, what else do we want to... yeah, that was it. So the way we're going to store this, because storing spheres on disk would just be like tons of memory. So we'll probably just basically, each volume is, yeah, so two things we've got to think about. There's this thing and probably the animation. So each volume, so volume you can think of as like a mesh, I guess, in a way, but not of triangles, right? It's spheres. So maybe another way you can think about it as well is like a sparse grid. Not really. Not a sparse grid because it's maybe. So sort of like the volumes are stored as a list of edits, and these are evaluated into the sort of octree at runtime. So when we boot, when the volume needs to get rendered, you got to sort of decompress it from a bunch of edit operations into this tree. So we kind of had that working, but we've got to make it work without the limit of 256 cubed volumes. Right, catch you around, Saul. Have a good one. Good to see you, my friend. So the other thing as well is about animating this thing, right? So I was thinking maybe each volume gets a bunch of bones, right? But the way you can think about a volume now, which is really great in this new design, is it's a kind of a encompassing set of spheres that can all LOD down to you can get a level of detail down to LOD 0 for that volume, and that's kind of like what it's kind of a good way to think about it. Like when you're creating something, you make a new volume now to say, hey, this is the sort of all of this stuff within here. When I sort of zoom out, it can all sort of it can have levels of detail together, basically. But you can split stuff into different components and share them. Yes, and this is another way. Yes, there's that thing to think about. But also, you pick a volume as well when you want to have instances of that thing. So say if you want to have like, say if you make an arm, right, and you want like so it's a lovely arm, or whatever. So say if you have like an arm on a character, it's even worse now. But anyway, and you want to replicate that, you can make that as one volume, and then do an instance on the other side, right? It's just got a different transform. So if we were going to allow for that to sort of save on memory, and you just have like mirror flipped things or something like that, there's two things that you need. The first thing is that you need to have like your sort of like the sort of the bone system needs to be independent of the volumes, right? And also you might want to color it in differently. So we were fixing that issue with in the previous design by having like a material palette, and you have like 16 materials per volume, and when you paint down, that's 4 bits, right? Kind of nice. When you paint down when you paint down your sphere, you select from one of those 16 materials on that single volume. And I think that's enough, because then that's four bits per sphere. So that's another thing we want to refer to as material palette, materials. We'll do a PBR thing. I'm not sure about procedural textures. Maybe. Or maybe it's just a texture. Right, let's just write texture. Maybe procedural, right? That's the bit we're not really sure about. So do standard PBR setup. Then we've got to get that material. Each volume can have a default material palette and can be overridden. Yeah, this is something that we're keeping. Magnificent. Yeah. Gonna be awesome. So each volume can have a default material palette. So if you duplicate the arm, right, it has a default scheme, but then every instance can just basically swap out the 16 colors, or materials rather. And it just means that we should be able to get, without creating different models, or different versions of the model that literally just have different painted spheres. The idea is you've just categorized the spheres effectively, and you're just, changing the material thing for that. And another way is we could have maybe, I think that's the best way of doing it. So yeah, there's something about this then, is when you do a lower LOD of a cluster, well, that's not really a good way of saying it, of a 2x2x2. So we still, even though we have a 4x4x4 or an 8x8x8 set of spheres, a sphere that has a, let's get the drawings going. So even though you have like a 4 by 4x4 set of spheres, right? And that's a cluster. Each sphere, and then because it's an octree, right? Okay, it's an octree. So each sort of, you can imagine each area from within this cluster has another 4x4x4 in it, right? So if this is a 4x4x4 in here, and in this LOD there's 2x2 in this sort of thing, well, it means then that 2 spheres, 2x2x2 of spheres in this octron, whatever you call it, I don't know, will then collapse down into a single sphere in the higher LOD, right? In this whole LOD here, which is great. So now, how do we do the material? Do we just pick the most prominent material? I think Ross Musco came up with the idea of we basically combine the materials into temporary runtime material. But yeah, I had a question about memory, but maybe that it's just a couple of pairs. Yeah, how many configurations would you get? Anyway, it's something to think about, at least. If you get textures involved, it might be a bit weird. Yeah, maybe. Or maybe you have multiple multiple materials or something like that. But for now, we'll just pick the most prominent one. Okay, so that's a great thing we're still keeping. So anything else about those materials that I wanted to move over? Did the edits thing. We're not doing 256 cubed. Right, so that was an issue when we built the BVH. We needed to use more than 30-bit. So it's 1024. You do your... Yeah, but we just do it per cluster now. Yeah, we might just build a BVH tree per cluster or something. I don't know, we'll figure it out. Future Henry's problem. I don't think any of this stuff applies anymore because it's all variable sized. Right. Good. So a volume instance. Right. I guess we'll keep these details. Right, so cluster means this. Material palette. Volume instance references of a volume ID, right? And material palette. So we still do that bones thing now. And then I think we're going to call them bundles or something like this. It could be called anything, right? But they're just basically another tree. This is not really part of the GPU. GPU doesn't care about this. But it's just a way of like organizing volume instances within inside a tree. So we might have another thing in here. So this is where I might think about looking at Blender basically. Because Blender has a sort of hierarchy system. And they call them collections and not bundles, right? And they have like a mesh. And they also have like a sort of a bone system in there as well. So, but yeah, we don't want to limit our volume to have just the set of bones that just control that whole volume. Because remember what I said is you now decide where you break the boundary of a volume. It's no longer a 256 cubed thing. There's two things, right? There's to do with you run out of material, palette, right, slots or whatever. You want to reuse a whole limb or something, and have instances of that and save some memory or whatever. Or the other one where you want to, when you zoom out, everything in that volume can basically go up to a lower level of detail or go down to a lower level of detail and combine together, right? And the volume is the boundary where all the LOD thing stops, right? And you can't go up any higher. Or you can't go up to a lower or down to a lower level of detail. So bones, if we keep those inside of a volume, well, you can't have arms that are instanced. You can't have, instances of things that are then part of the same sort of animation kind of system, right? So this is where I've got to have a bit of think how that's going to come in. And then basically we can just plan out all the shaders. Because we've already written this, right? Version 1 of it and found the problems. So we should be able to basically nail this plan now. Hey, it's been a while. You guys working on the spec for a level of details? Yeah, so we wrote up an initial one, and I spent like 14 streams doing it, and we got it up and running, and it was a bit buggy. It was still buggy still, but I was looking at the performance stuff, and I was thinking like, there's some clear design things that are a little bit off here. So I basically spent the whole past couple of days just thinking about it, and we've come up with. I've gone away and done some sort of research, and found out how we can basically improve it. So we're just gonna do a redo of the system, um, and remove some restrictions, and just make it an all-round better system. It should be a scalable system now, because I think I could have maybe made that system scalable, but it wouldn't have been. It would still have the restriction issues of each volume being 256 cubed, and it probably could have been faster as well. So just fixing all that up in one go and having a second attempt. So we have this sort of bone. Yeah, because like the worst thing is, right, is we can keep going down the route I'm going, but then I'll probably have to do a big redesign of it anyway when I get to a certain point. So it's just, taking a step back and sort of analyzing what's great about it, what isn't quite great. And we've got the code still, so we can basically just like reuse parts that make sense. So it's not like we're going to do a complete from the ground up rewrite. It's just going to be, just rework the parts that are not doing so well. Yeah, if you're interested in more of the details, you can check out the VOD on the VOD channel or on Twitch when it's finished. Hey, collector of stuff, how you doing? I've been watching your streams a few times and I said to myself, wow, nice beard. Getting a bit crazy now though. Yeah, don't worry about it. Actually, I'm just letting it grow out because I'm being lazy. And Sunday. Is when I'm just gonna get a full-on haircut and just get it all, shave everything. And not necessarily my hair though. I'll do the classic sort of 3 on the sides, and I'll take about half off the top, But yeah, because I'm going on holiday the whole of February. I'll be away. So the whole of February I'm in Australia. So I need a nice fresh haircut where I'm not going to be, dying of heat exhaustion. Thank you, Sophie. Appreciate it. Lovely beard. Also a bit ginger as well. So with the bone system, right, essentially you'll have different volumes. Let's draw a little guy. Let's draw a torso. Alright, it's got a bit of a... Right. My drawing skills are about 5. Right. Maybe he's got some shoes. There we go. Maybe he's got some eyes. Anyway, he's got a nice big smile. That looks weird. Anyway, so basically, imagine this is a volume, this is a volume, this is also a volume, and this is another volume. So each limb, and maybe the shoes are volumes, and maybe they're instances of each other or whatever. To help save some memories. Now, you want to have like a bone system, right? So you have like your bones. And they sort of affect the spheres within this. It's like a road. So one of those like, man, what was it called? Micro machines. Yeah, like a micro machines level where you're like just, anyway. back in the day on Sega. Micro Machines, good game. So, and maybe have a bone up to there, I don't know. Thanks. So the idea is this bone system needs to work. You know, it's a bit like in Blender, right? Where you got these different, you have that sort of, I think it's called like an armature or whatever. I don't know what it is, but or a rig, whatever it's called. No, yeah, something like that. I need to get the terminology right. So, but yeah, so the idea is this this system has to be like when you have a volume instance, you need to know, hey, these bones here are like because with triangles and stuff, they just do bone weights, isn't it? Or maybe you put them inside the volume, the bones inside the volume. Ever think about it. Hey, Psychode, how you been? Yeah, here you are. Smiley face. Maybe you got some hair as well. Or maybe you got a hat. Wait, give you a baseball cap. I can draw, I swear. Okay, this is going poor. No more. Busy but great, awesome. Yeah, I've been good. Same, super busy, but it's been going awesome. It's been working, looking after the baby, streaming, chilling with my wife, going out with my friends actually. Went out with my friends and got hammered last week. And yeah, it's been awesome. Been amazing. Just spent 14 streams writing a first version of this LOD cluster system. Got up and running, not kind of. It's got some bits which are great, and we learned a whole bunch. But there's some certain aspects that I don't want to change, and make it go better because it's not fast enough at the moment. But it's going to be awesome because we've got it all planned out. So yeah, well, we're still planning a bit out, as you can tell with the bones. But yeah, we just got to figure out because in Blender, right? They'll like they'll they have they paint on bone weights, right? So you have like a triangle. You have a triangle, maybe there's another triangle there, or whatever. Say this is like the middle of the arm, and there's more of the arm. The arm goes down this way, arm goes down that way. You have a bone that sort of goes over here. Oh, whatever. You have a bone that goes like this, and then maybe you have another bone from the hand going like that. I don't know. There's a thing called they paint weights on the vertices. So they go, hey, this vertex position is, and you're painting weights where you're going 50% of this position is defined by this bone. 50% of, is that right? Wait a minute. I forget the exact. Yeah, it's done by this bone. Yeah, and then like 50% is by this bone. Whereas you might have like a vertex over here where you're like, 100% of this position is controlled by this bone. and you have basically a little list of weights, and a little list of bones. So the question is, right? Usually you create like a rig, isn't it? And the rig means that you can animate the rig, and then it can apply to any. Like you can just make another sort of human being, and the same rig can be placed on that model, and then it can be use the same set of animations. So I don't know how that system's going to fit in. Yeah, we might have to have a little set of bones per sphere, maybe, or per sphere would be way too much though. Maybe per cluster. Maybe per cluster, we'll think about it. Yeah, weight to the bone, exactly. So it's like how many bones do you want to support and per what? So you can do like, I think some people do like 4 bones at most, and maybe 2 at least. But you don't do 1 bone. Yeah, per vertex weight, exactly. So the issue is here, right? Our vertices are little spheres, and we kind of want to have a whole bunch of them. So let's go to our current sphere. Yeah, I think we can figure this out. This is going to be great. Because the thing I really like about doing it with spheres, like I don't care if they becomes little holes and stuff, because we should have some bigger spheres behind it. And so we should be able to get like a volume that's been able to be like rigged and stuff, which would be pretty fun. So if we go to our sphere, I think I call it like a volume sphere. And it's like this packed thing. Turns out I didn't even use a lot of the bits in it. So the max number of bones that can be attached depends on the implementation. Some can be convoluted up to 8. Yeah, it does affect performance because you basically have to. You get 8 different matrices, and you sort of weight. You take a. Yeah, you've got a weight, isn't it? So you take a ratio of all of those, and you merge them all, or something like that, isn't it? Yeah. So ideally, this sphere, I got down to 16 bits, and then I realized that hang on a minute, I don't even need these guys, which were like 1 bit each basically, because you can implicitly get that based on the index within the cluster they're in, right? For some reason I underlooked that. You don't need the LOD in there as well, so you get rid of that. There's the material palette index, that's only 4 bits. Auto-generated LOD probably doesn't matter. The exist bit, we'll probably need that. So that's 5 bits that we've got so far. So if we try and stick within that limit of 16 bits, the problem is, right, if you have like a rig, so you could quantize weights down to a byte each, and that's 8 bits. Yeah, we can't do that then. No, you can do it. Easy. Easy. I got it. Each cluster. Yeah, but it's difficult because you have LODs. Each cluster can have 16 bones, right? So each cluster can support 16 bones. And they use 4, so you get a layer of indirection, maybe. So you use U16s for bone indices, and these sit at the cluster level, right? Now each sphere gets a cluster bone index, and that might be. So sorry, how many we're gonna do here? U16, you might have 16 of those. Yeah. This is just a thought at least. Then you might do a U4, right? 4-bit, right? Bone indices index, and you'll have bone indices. These are great. There are 2 levels of indirection. And there's maybe 4 of those. And then that's 16 bits, right? And these will be sitting inside a sphere. So you've just spent or you can have the bones. Let's have a think about it. But it becomes really obvious, right? When the bones, if you have a bone per cluster, yeah, so you have, say you have a bones per cluster or whatever, it becomes painfully obvious. Like all the spheres in a cluster will move together, and they're not going to move independently. Maybe. Didn't. Good joke. So bone indices. Then if you have those per sphere, like I guess we could just or maybe we share them on a 2x2, but then still it's going to look painfully obvious when you have 2 spheres. The 2x2 spheres basically moving together and looking like they're grouped together in a weird. It might look weird. Maybe. But again, it only looks weird if they're uniformly laid out. But I was thinking we was trying to like do a thing where we might kind of offset them a little bit to sort of make the spheres instead kind of go together a bit. I don't know how we was going to do it, but I forgot now. But basically offset them a little bit so they kind of pack together, but they're still on a grid. But maybe just offset them a bit. I'm not sure how I'll do it. So maybe if you do the bones per so if you had the bones affect a sort of quadrant instead, that would be so you have 4 bones, right? And then you have the bone weights. And this would be like per 2x2x2 set of spheres, right? So if you did that instead, right, how much is that on average per sphere of memory? So on average that would be so you got 8 bytes for that, right? And then you got a further 4 bytes. That's 12 bytes divided by 4. So that's 3 bytes on average, 24 bits. On average, you've just done there. But again, maybe you could quantize it down even further. And you know, have bone indices again. This is 4, right? And you do a maximum of 16. Right, and these are shared in a cluster. Right. Is that right? Wait, 16 is way too many because you've already done 16, 256 bytes. Or bits. Isn't that 64? No, 32. 32. Yeah, I don't think that's going to save you any memory because that's 32 already bytes. Or the other one been 24 bytes times 4. 96 for the whole cluster, that would have been the other version. There's already 32 plus, what is this? 4 bits, that's 2 bytes. 2 bytes times, 2 bytes plus 4 bytes, 6 bytes times 4 plus 32. So it is less, it's 56. It's 56 bytes, so on average, so that's for a whole cluster of, was in 4x4x4, as an example. Wait, I got that wrong. I got the numbers wrong. Did my maths a little wrong. So it was 24 times by 8. Because there'll be 8 2x2x2s and a 4x4x4. Right, 100. So if you were just to have bone indices and weights, it would be 192 bytes per cluster. So yeah, if you have these like, wait, there you go. Per 2x2x2 set of spheres. Wait, did I do that calculation wrong again? Hey, look, I'm on no hands. Hey, Kappa. 56 by 96. 6 going to speed up. Yeah, we're trying to save memory here. This is the problem. We're trying to push tons and tons of spheres. So we're paying the cost of a slight indirection. But it'll be cached anyway. But yeah, so sort of just saving tons of memory when you make it large scale. I think I did my math slightly wrong as usual. So it's 2 bytes times 4. Right, so you got 8 there, then another, so that's 12. Right. 12 bytes per 8 spheres. And you times it by 8. 96 bytes per cluster, so maybe that was right. Now, if you were to have, yeah, I think this doesn't change anything. from my understanding, right? So you would do 2 times 16, obviously 32, right? Plus, so you got 2 bytes, 2 bytes for that, and then plus, so 6 bytes. 6 bytes per 2 by 2 by 2, so it's 8, 48. So plus 32, that'll get you to 80. Ooh, tiny bit of savings. Is that right? That's 2 bytes, right? They're 4 bits packed. There's 2 bytes of information. You got some weights. So you might be able to pack the weights down as well. Right. See the weights. If you like, they're just basically a 0 to 1 value, right? So if you're making each weight, that's 256 range of values. But if you did 16, that means the step size is that like what? Please get the calculator. That one. The step size would be 0.125. Is that right? Something like that. I wonder what over 16 is. Yeah, so that's the sort of step size. So you got 16 different, hey, I'm like 2/16 of this bone, and 4/16 of that other bone. And maybe that's a way of packing down the data even more, right? Halving the memory for the weights there. Yeah, awesome. Do you happen to have any good tutorials on bit shifting and masking? That's one C topic that keeps destroying my brain. If you're referring to some of the stuff that we did in the past few streams ago, that was destroying my brain too. And that was, but yeah, I do understand when you first learn bit shifts and stuff, that is, that stuff, it's a little bit weird to pick up on. But as soon as you've picked up, it's honestly, it's a walk in the park. The only thing is like right out these requires a bit of thought sometimes, but nothing too much. Be a bit shifting like and or XOR. These sort of operators are not. These guys be a walk in the park when you find a tutorial. Although I don't know of any good sort of tutorial for them. I can't really. I'm gonna have to sort of just Google search basically, but I'm sure there's plenty of stuff out there that'll make it click. It's very easy when it's laid out in a table, basically. Most of the issues are sort of translating hexadecimal into bits and doing it that way. But as soon as you get the idea for it, just Google for it, man. If anyone has any other good ideas, or if you're a Gen Z like me, I'm part Gen Z. I'm sure there's plenty of good YouTube videos you can watch as well. But yeah, I don't have any specific links though. Oh, there you go. There's one from Cranston over there. An advanced reference. That might be fine. Well, okay, maybe. Oh, is this all the bits within it? This page is good. This is a good page. I forget this page exists. Put that down. This is a good page. But yeah, these are all little hacks you can do. But yeah, this is more like of stuff you can do with them. But yeah, I strongly recommend checking that tutorial though, because I don't think you're going to understand this too much. But if you can do those tutorials and then come and visit this page and try and decode what's going on, then you get it. this would probably be a good way to check how much you really understand, basically. Where did music go? Part boomer, part zoomer, exactly. Best of both. No, actually part millennial zoomer. Boomer's the gen above me. Nah, there's plenty of tutorials out there. Like, I can break it down like dead easy for you here, right? So you have 0, 0, 0, 0, right? Or 0, 1, 0, 1, 0, 1, 0, 1. So, so this in hexadecimal is 0x. So there's the 1 bit, there's the 2 bit, there's the 4 bit. So 4 plus 1, right? 5. Right? That's 0x5, yeah? Now, when you do an AND operation on this, what do you get? Well, you get the same thing. What happens if I was to get rid of this bit down here, right? This will now become 0x4. So you're ANDing 0x5 and 0x4, right? What do you get down here? And the answer is 0x4, because it's doing an AND of all the bits, right? So 1 and 0, 0. 0 and 0, 0. 1 and 1, 1. Right, so AND means that you have to have 1 on the left and 1 on the right, and then that column will be a 1. You have OR, which basically means like, hey, so in this case, it'll be this number, right? Because 1 or 0, if we have 1 or a 0, we get a 1, right? And then if you have a 0 or a 0, you get a 0 because there's no 1 in either of the ones left or right. When here, right, you've got a 1 or 1, well, that's obviously a 0 because you have 1 or sorry, if you have a true or true, 1 or 1, so 1. Now, there's a really awesome one, which takes the word OR and gives a bit of a different spin. That's XOR. This thing is amazing. XOR is amazing. You have to use it in a program, every program you write. And if you haven't used it, you're missing out. So XOR, it's basically like OR, but instead of saying, but it only works with it only gives you a 1 when there's a 1 and a 0 on either side. But if you have 2 1s on either side, so let me update this. There we go. If you have 2 0s either side, or 2 1s either side, the result is a 0 in the bits, right? But if there's a 1 and a 0 on either side, so if it's had a 1 down here, yeah, 1's on the other side. So it's an exclusive OR, meaning exclusively it has to be 1 and 0 for the bits either side, right? So 1 this side, 0 that side gives me a 1. 0 on this side and 0 on that side gives me a 0, obviously. 1 and 1, this is where it's different, gives me a 0 instead of a 1, right? And then this one is 0 and then 1 gives me a 1, right? And that's basically bits for you. That's the whole, that's the whole thing. You've obviously got the NOT operation, which inverts everything, but there's all the binary ones. Because it makes it easier to write. Like, hexadecimal is shorter. And also, it makes you seem cool when you know something other people don't. That's another thing about it. But yeah, that hex is old. Doesn't work. But yeah, like, hexadecimal means you can basically represent 4 bits with every digit. Right? So this gets you 2 bytes. you can represent 16 bits with only 4 characters on the screen. That's where it takes away. And it actually isn't too bad to read. It just requires a bit of thinking. But, within, by the time you become 50, you'll be read like English. Or you could do 0B in other languages and do, have really wide code. But yeah, highly recommend you watch that back, or take that sort of snippet you've just seen me go over, and then pick up on how someone else teaches you it, and it's basically that simple. Like, as soon as you know those things, everything just becomes easier with bitwise stuff. Oh yeah, it's not equals. Yeah, definitely. It's another saying XOR, so not equal. So yeah, that's a good way of saying it, because if you have two booleans, A and B, and you go A and B, when A and B are true, you get a true. When A and B are true, you get true. When A or B are true, you get true. For an XOR, you don't get exclusive XOR because it doesn't make any sense, but you can kind of get one. Exclusive XOR is just not equal, right? When A is not equal to B, meaning A or B is... So if this one is 0, and this one is 1, you'll go through. If they're both 1, right, you don't go through because they're both equal. Yeah, that's another way. That's a good way. I like that description. That's good. There is a neovim, but for C. Yeah. No worries. So yes, we quantizing, right? So 4 times, or 2 times, yes, that's 32, right? Oh, you'll quantize this down. That's 2 bytes each, so it's only 4 bytes, times by 8. 8 2 by 2 by 2s in a cluster, for instance. 32 plus 32 is 64, right? Cool. So you're down to 64 bytes a cluster for these bone informations, which means then if you've got 64, right? 64 spheres in a cluster, that literally gets you 1 byte per, on average, 1 byte. Wait, how does it get you 1 byte? This is all wrong. What is going? How am I? Oh yeah, because this is per 2 by 2 by 2. Yeah, so on average, 1 byte per. No. Yeah, no, that's fine. That's fine. Sorry, this 3D and it's confusing me. Yeah, so on average, that's 1 byte per sphere for bone information. If we were to make this be a 2 by 2 by 2 per 2 by 2 by 2 of spheres, we could times it by 32 by 8 and then add 32. And that's how many it would be if we did bone indices per sphere. It would be that many bytes per cluster. So that's big savings there. But the only issue is we could get some issues with the we could get some issues with the, when you transform, say you got this like bone or whatever, I don't know. You can when you move these 2 by 2 by 2 of spheres, they will move together, but the other 2 by 2 by 2 in the same cluster will move slightly differently. And it might look very clear. There might be very clear gaps, right? Like this. that emerge. Whereas if you did it better, these things would sort of like these things would smoothly happen, right? You would get a sort of smooth set of gaps or whatever like this, right? So that's a problem when you sort of do stuff like that. I guess could we quantize it anymore? So this means you're 2 bytes for there. It was right when it, yeah, okay, I do get it right. Right, so that's 4 bytes of bone information per sphere. And was trying to make it fit into like 2. There's only way to quantize it anymore unless we did. So if we brought this down to a U2, that would be a byte. But then you've only got 2 bits, which is like you're dealing with quarters then, right? So you're saying, hey, the weight for this bone is a quarter. Right, and the weight you're painting down is in quarters per sphere at that point. So I don't know if you're going to get then the trade-off you're making there is sure you can pack more right, sure you can pack this information better on your spheres, but it means when you have 2 bones that affect the same set of spheres, which might not be that often. Maybe. I don't know. We'll see. We'll see. Probably is. No, of course it is. You get it. Sorry. Don't mind me. Like, between 2 limbs and stuff, right? But anyway. This is a bad example. But yeah, you would say, like, hey, this one has 3/4 of that one, 1/4 of that one. But it's really. You're painting down quarters at that point. Of weights and stuff. But the weights don't have to be yeah, they'd be like a weighted average or whatever. Sushi. Does it look like sushi, yeah? Yeah, maybe this is okay. Let's just see how much information it is. Like when you're painting down, like you got your volume, you got your spheres down, and you're painting these weights. When you play out the animation, the sort of glitches you might get with such small amount of weights, or the artifacts you would get, would come from you would see a set of spheres. So rather than the spheres smoothly breaking apart, say this one gets 3/4 of that and 1/4 of that. There's no smooth in between where these two would break apart, if you get what I mean. It could be alright. It could be alright. Let's play with the numbers. Yes, you literally did it in quarters there. So you did it down to a U2. So you're packing that down to a byte, right? And your bone indices. So you've got 1 byte, so that's 3 bytes. But then if you pack that, you've only got 4 bones per cluster, maybe. I know you would get mega savings there. Let's take this one. This is another approach, right? 4 bytes per, and this will be per sphere now. Right, a cluster is like 4 by 4 by 4 or whatever. I mean, you don't have like, imagine those were U2s or whatever. So that has the restriction of, yeah, you only got 4 bones per cluster, which could be okay. And you still have up to 4 bones per sphere. Maybe. So that's 1 byte, 2 bytes. 2 bytes per sphere. Alright, 2 bytes per sphere. You got 64 spheres. 128 per cluster plus the plus 8 bytes. So 136 per cluster. Yeah, so that's what we're kind of looking at in terms of our options. Like, because ideally you want the weights and the bone indices on. Right, let's bring these over into the plan section. I don't know what we're doing, but specifically, but these are the sort of options that we have. Yeah, these are the options that you basically have. So the idea is you probably want like a rig or something like that. Or you probably have like a bone. Anyway, so you probably have like a um hmm. Let's just call it the bone system, whatever. So we'll have like, you have rigs and sort of animations per rig, something like that. And then like each volume of spheres. See, this is the thing, right? When you instance a volume, right? And this is where we went with materials. We went with a material palette. So when you have like a whole volume, of like an arm or something filled with spheres, rather than sort of painting down over the spheres and having some way of storing like, hey, this sphere here has this sort of has this color. We decided to have on each sphere have like 4 bits of information which stored like an index into the material palette, and you can swap out the material palettes. So with the bone system, it's kind of a similar problem, right? You can either have some form of like palette thing, or no. Yeah, basically, So, sorry, in your spheres, you basically store this weight information and the bone indices. Yeah, but what bones? When you're making your when you're making your like arm in a separate volume or whatever, you're just painting down the spheres, maybe decorating it or whatever. You're going to duplicate it. There's no concept of the bones or whatever, right? When you're doing this here, and these bones are different from these bones. So it's kind of like a thing you do afterwards. Um, so the way they sort of solve that in like, I wonder how they solve that with like meshes and stuff, right? Uh, or do you just stick it under a, hmm, or maybe we do the whole one rig per, uh, maybe one rig per volume. I wonder how they deal with that in like Blender and that. Um, they call it like an armature, isn't it? Um, so yeah, they probably have a separate set of vertices or whatever, but not sure. Gray mesh should be deformed with the armature's bones. I wonder how, like, because you've got multiple meshes that make up like a thing that can, like an overall thing that can get attached to this rig. So they have per instance vertices, maybe. How far away from implementing IK? Um, until we probably when we get the clustering system done. Wait, IK. Not sure how long after that. Probably not for a while. Yeah, I'm not sure what sort of steps we're going to take to get there. Probably just do skinning first and just stay with that. IK is only if we need it. I'm not sure we need it for the game, but we definitely want like skinned models. So vertex groups for bones. One of the main uses of weight painting. When a bone moves, the vertex around a joint should move as well. Just so that will mimic the stretching of the skin. Um, uh, hmm. There's something called like a vertex group. Hmm. Um, Because the issue is we don't have. Because the issue is we don't store the spheres on disk, right? We store the information it takes to create a volume, and then we build the volume up on the GPU. So if you're going to be having the weights on the spheres, it has to be done when you build the volume. Or maybe you could go over a volume. Or maybe for a volume, you could remember, for the volume instance, you could remember the painting that you do and have a series of edits that paint over. Yeah, that's the way you do it. That's the way, that'd be awesome. So like we store a list of like edits that get processed to like build a volume. It's not 2516 unless it's garbage. We're getting rid of that. And then you sort of, build a cluster tree of spheres. When you have an instance, you can choose to have a list of edits which paint over this instance. So then that will compile down into another set of sphere information. So you need another set of... Oh, but then you'd need another cluster tree. Which could all use the same cluster indices, right? They can all use the same set of cluster indices. But you need a mirror tree. So theoretically what we could have is... So for every instance that's sort of boned or whatever, it would need to have each volume instance needs to have it will have like a animated volumes. Or we say rigged volumes. Yeah, rigged volume instances will contain we'll need to build a sort of parallel. I'm trying to spell today. We'll need to build a parallel octree of clusters purely with the bone weights, right? That store the bone weights. The bone indices and weights. That's really cool. Because it can be compressed down into the same system and stored on disk. And then also built, and we can reuse these octree clusters of where the spheres are. See, what information do you need to keep now? You just need to know there's a sphere there, right? So you literally just need a bit set. The material palette could just go. Like, we literally don't need a material palette anymore. Because I think we can do this same idea. This would be really cool. So rather than doing... rather than having a material palette, even though it is kind of cool how you can just swap out, instead, you can just... when you have an instance, you might have a base set of paint, right? There's a bunch of paint edits down. Where is it? So there's when you're sort of doing your edit operations, there's a separate list. Oh, no. The initial list that you've painted out. So where you're on the base paint, do you want a separate list of edits where you paint and see the edit? Because the issue with that is you can't undo it. You might have two different undo stacks then from the main edit stack, which would be a bit weird. Or no, you don't necessarily have to. But if you have a separate paint stack, you might have sort of a set of paint operations. So they have has a volumes have a default set of paint operations or something like that, and maybe the paint operations a default set of paint operations that sort of color the spheres of a volume instance, right? So each volume instance has a parallel, right? They all have a parallel octree of clusters that store the material, right? And maybe you have do you want to blend materials together? You could do that, right? Where you have, hey, it's 50% that, 50% the other one. Or layers of materials or something like that. Per sphere might be a bit too much, but it could be possible. And if you do that, blends of materials, you can do the LOD thing a bit better. Lower level LOD thing a bit better, maybe. But this is a good solution because then we can get rid of. You can still have the palettes, right? So when you're doing the painting operations, you still might have, like, hey, I've just painted this volume, and I've got a bunch of edits, and they use a palette, right? So still use the palette. That use the material palette, use a material palette to reference materials that get assigned to the spheres of a volume instance, right? So there's only an octree. It's like an octree where it's like a bit set to store which spheres actually exist or whatever in the volume. That's the only thing that's shared. But the colors, maybe. Is that per instance data though? You've just basically made it a ton of per instance information, which could be a lot, but maybe it's deduplicate. Maybe you share them. So maybe we can have a thing called a well, if you make it per instance, right? It means you could have some gameplay stuff where someone has like a you know, you can literally just paint over your guy, right? A material. When you're playing, which could be pretty interesting. Yeah, but I wonder how much information. So obviously we do want to share when we can, right? So you have like these edit things, and they paint some octree of, right? So I think I might call it a material tree. Wait, what should it be called? Is it like you maybe call it the material tree. So this is an octree of clusters that mirror a volume's clusters. So when you create this thing, you basically just copy the cluster thing, but then it has an extra bit of information in there, which will store a bunch of materials, right? And you want to say like each sphere. See, I don't know about this, right? We could do multiple materials or has a material. To be decided, multiple materials, right? Either blended or layered, right? We've got to kind of research and think about that, right? But there's this sort of material tree. So volumes have a default set of paint operations that, right? So those store material indices, palette, material indices. To be honest, to be decided. To be honest, yeah, that's a good discovery, because that means that we could. It opens up the gate to just sort of like. So they are used to. Right. A material palette. But they also have a default. They also have a material palette. Has a material palette that each sphere references. Yeah. Volumes have a default set of paint operations that use a that are used to construct a material tree on a volume instance, if not overridden. So you'd have like this material tree which is basically an oct tree that mirrors the volumes sort of cluster tree. Yeah. So maybe we should write the word cluster tree here and just sort of say it's just a an oct tree has a cluster tree, something like that. So it's just an oct tree of clusters. Whereas it like each thing can have of clusters, and the clusters is up there where we say 4x4 of spheres. Whereas an octree node. Excellent. Yeah. So the beauty is, right, you can share the material tree if they've used the same set of paint operations, right, over a volume. But if you choose to have a different, but if you use a different set of operations, so there's two things which is cool about this, right? You can use the same material tree and swap out a material palette. So the material tree stays the same, but this doesn't have a material palette, right? The material palette comes from, right, uses the material palette from the instance, something like that. Yeah, so you could basically have like a volume which decides to get painted one way completely differently, but also you can just swap out and get different color schemes, and those can all share the same tree of data. But also, if we want to, a bit like with animations, you want to minimize the amount of like per instance information there is, because it could be quite a lot. You don't really have typically tons of animated meshes going at the same time, for instance. So like that, you could say if you have the main character and he falls over in a bit of mud, he could get painted with a bit of mud, right, on top of, and he just gets a different material tree. That would be pretty neat, right? That'd be awesome. What did you think of the video game Spore? Yeah, it was pretty cool. I played it when I was younger. It was a cool game. Like, I really liked the base game, was cool, and all the DLC that they brought out was pretty cool. There was one when they made you go down on the planets. It was one of the final DLCs. And it wasn't. I think they could have explored that a bit more, but the rest of the game was just incredible. Like, make your own creatures, and like they extended it with the different parts you get with the DLC, with like this exoskeleton stuff and that. It was good fun, and I think I think some of the first stages weren't. Um, yeah, I think that the thing that kind of sucked is you can kind of like well, yeah. You always have to advance to the next stage, so you have to sort of restart if you wanted to play one of the stages again. But yeah, I really enjoyed it. Is it a game that you've played a lot, Kappa? Yeah, it was a long time ago now, but it's very impressive, like that game they made back in like, when was that? So 2006 or something? Forgot what that was. Um, so yeah, we have this material tree. So per instance, um, it's not, but it's the only game that got me curious about animation stuff. Oh, you should bid it up and give it a play. I wonder how it holds up. So each instance can get a parallel tree that stole the material. Right, it can have has an optional material palette override. So you can override the materials, get different skins and stuff, right? For instance, uh, you can. Do you want to call it a material tree? Yeah, has a material tree that is either shared between instances, or is per instance, and editable. That would be amazing. That'd be lit. LOD. So with a bone system, then we'll need to build a parallel. Right. So it's not really. I guess it's the material cluster tree. We'll call it. So maybe we'll say with the bone system or whatever, right? You have you have your bone cluster tree, an octave cluster that mirrors the volumes cluster tree. Uses do you call it a volumes skin, or we need to have something where Um, yeah, I might call it a volume skin. And the volume skin might be called, and you can have different, but it's not really a skin, is it? What's the way, volume paint. Volumes have a default set. Okay. Have a default volume paint. It's an easy way of piling it down. Volumes have a... No. So, a set of paint operations. They use to construct a tree. That can be shared that target. So this sort of targets a volume. But they sort of are applied per volume instance. That's a good way of saying it. They're applied per volume instance, and they have a default material palette. Or volume. Yeah, use it from the volume instance. Hey there, Metamente. How's it going? Thank you so much for the raid. Appreciate it. How you been? How did stream go? Hey there, Omni Digital. Welcome, welcome. Just we're just working on. So we got a sort of LOD cluster system up and running. Discovered there were some problems with it, but kind of super happy with a few things about it. But there was a few parts that were kind of making it a little bit too slow, and I kind of had a restriction I wasn't too happy with. So we're redesigning it and going for a V2 and just ironing out all the kinks. So we're just planning basically how we're going to render a ton of spheres. So yeah, if you're interested in like how the stream started off, we do have a VOD channel, which I'll be posting up on the VOD channel on YouTube, or you can check out the stream and play it back. But we went over from the beginning, like where the issues were, and we've just been basically doing this plan ever since and discovering how to make it even better, basically. So yeah, I'm super excited about that. Cluster tree thing. Volume paint. Right, default volume paint. Right. Well, we could call it volume texture. But then the texture is made by a bunch of paint I don't know. Paint. Yeah, paint makes it seem like a single piece of like color of paint, right? We should call it painting. Look at me go, I'm on a roll. On a bloody roll. Right. Volume paint, that's really cool. So in terms of like, when you have this doesn't apply anymore. So we need to think about when you do lower LO, we need to think about we need to think about lower level of detail. Each volume can have a default. No. Each LOD of a 2x2x2 sphere set of spheres will make set of spheres will this reads wrong. Each lower LOD of 2x2 set of spheres will be taken to make will be used to make sort of a sphere in the parent cluster. Either use the most prominent material from its children. But Rosmosco came up with an idea where we got like combined materials into temporary runtime material, something like that. But also maybe like there's another one like maybe they get layered, blended. Yeah, that's more like a blended idea. That's fine. Anyway, stuff to think about. I don't know what we're doing there, but that's good. So reduce that down now to simple, so other concepts which get reused and that, which is really great. So we're still going to roll with like a bone system. We have rigs and animations for each rig, right? This is like how the bone cluster tree is going to work. But yeah, basically you have a sort of bone cluster tree, is an octree of clusters that mirrors the volume cluster tree. Uses a material palette. Wait, what's that on about? No. Right, as a copy. So basically we're saying each sphere has, right, each sphere has, right, it's something to do with this code block here, has one of these sphere / cluster, has one of these implementations below. I don't know yet. We'll decide it when we actually write the thing. So we'll put that in some form of little code block type of deal. I don't know what I'm doing. So depending on how much memory we want to use, but that's super cool because we can just build these. And what's great is if you have multiple, this can be shared. So you have multiple instances or multiple, oh, wait a minute. Bone cluster tree. Yeah, this could be shared between multiple instances of the same yeah, we'll figure out how this attaches now. So you want to say like a bone is like, you know, maybe like a matrix. I forget the yeah, matrix and with a parent bone, isn't it? That's the structure, isn't it? So a matrix basically it's like, you know, bone from parent matrix and then a parent bone. I think that's it. I forget the anyway. So you have a rig which is comprised of bones basically, like a bone hierarchy, a bone tree. This is a tree of bones. So there's a bone tree, is a bone tree or tree, yeah, bone tree, something like that. And then you have like animations, which basically like so animations like belong to a rig and sort of transform the bones, right? Well, anyway, whenever we get to that. Okay, so I'm glad we've nailed that down a bit, right? So these are the implementations where we can decide which one is best and work out what the so they each have their own issues. So the volume instance. Now the beautiful thing is about this is it can have a shared. The volume instance can have so when I say like rigged instances, we'll reference a sort of shared bone cluster tree, where it is shared between volumes, which is potentially shared, which is potentially potential. Wait, there we go. Which is potentially shared. Again, saves some memory, which would be super nice. Anything else that I'm forgetting about this bone system or material? Yes, you got the material palette override for that sort of cluster tree, so you can basically have different colors for the same. Wait, there's a new word for it. That are constructed. They're used to construct a material cluster tree. So you basically apply. It has a volume painting that is either shared between instances or editable, and then you can apply the palette that they use to paint. That'd be sweet. Right. I think that is the sort of the sort of definition of everything that we want. Now we've just got to write the plan on how to build it. Have you seen Static? It's an OG game from the DOS era where everything is made of ovoids. Albert, most of it is pre-rendered. No, I've not seen that. Let's take a gander. Oh yeah, no, I may have seen. I don't know. Am I not signed in? Please don't be signed in. Good. All right, let's take a gander. Well, you're saying a lot of this is pre-rendered. Ellipsoids, eh? Ooh. So this is what we kind of want to be using as ellipsoids in the end. I'm not sure. That's kind of cool. We're not going to be doing them like this though. They're a bunch of spheres in a volume. Maybe we might be able to use ellipsoids. Like, when you transform the model, things will end up being ellipsoids because they'll have non-uniform scaling. But I don't think we'll be doing stuff like that because the idea is just able to paint these things down. But that's pretty cool though. That's neat. Mm, that's great. Yeah, like theoretically, if you wanted to make that sort of spider thing like that, you kind of could with the ellipsoids by just doing one sphere and stretching it, and then just rigging it or something. I don't know with this design, but um, yeah, pretty cool though. But they get so teeny down here. It's impressive for the time. So you're saying a lot of this is pre-rendered backgrounds, and then the only thing that's rendered at real time is these low, quote unquote, resolution versions, right? It is, isn't it? That's cool. I knew someone had like done stuff like this before, because everything you've already thought of is done. It's been done in the past, but that's really awesome. Yeah, so they'll do it for collision and stuff. A low resolution thing. That's cool. But yeah, pre-rendered backgrounds, I can see it. Still there. It's neat. Um, so the interesting thing is they're sort of layering these things like this. Um, they overlap quite often. I was thinking maybe we can choose how big the balls are in each grid cell, maybe. Um, as well, that might be a thing we might choose to do. Um, but doing like ellipses like this, you'd have to put them in a single, like, I think Russ Musco was saying you could use ellipses to like make grass basically. And it could be possible you just paint down a little 4x4 volume, right? And then just stretch it along an axis, and then there's your grass, right? Um, but again, you could do two layers of it, stretch it along one axis, and then use the bones, and then do boned animation with a few of them stretched, right? And then you could just add more layers and more bones, and you'll basically get some like interesting looking grass, right? Or more spheres and yeah, and bones, whatever. So yeah, it's possible to still use ellipses, but you just have to stretch it. There'll be spheres within the cluster tree, but with the non-uniform scaling, they'll become ellipses. That's awesome. That's a really cool link. Thank you. Um, yeah, so what's left now is we want to design a way to make this. And since we've done the initial version, I know sort of like how to design this from now on. But I think let's give like a brief idea of what I want to do. I've got like 10 more minutes before I really want to come off. I need to chill out before I go to bed. But so the basic idea of like, yeah, we need to like have a volume constructor. and what are the steps to do this thing. So your volume constructor is now infinitely, right, so we're doing 4x4x4 or 8x8x8. I don't know which one we're going to do yet, but we're going to, we'll make it configurable at compile time. So bust out the big boy calculator. So if you do 4, so if you have like 8 levels of detail, that's not so bad. So you have 4x4x4s with 8 levels of detail. That's 65,000. You know, spheres. Yeah, the issue we're going to have though is the biggest problem you want to avoid, right? So 65,000 across one axis. The issue you want to avoid is this. When you have 1024, right, cubed of data, that's 1 tera. That's 1 tera of information, of data, right? Multiplied by whatever, however many bytes, and that's that many terabytes. Sorry, not tera. Sorry, I mean giga. Sorry, giga. Yes, it's 1 giga. So when you have 1024 cubed, it's 1 giga, whatever. So you multiply that by that number of bytes. It's how many gigabytes. The way we solve that problem is we simplify everything. So it's like as we build, what I need to make sure is as we build the initial tree from these arrays of edits, right, where you sort of paint down these spheres in these volumes. So you sort of paint down big sphere, ignore the 256 crap. That doesn't exist anymore. This will get filled with a bunch of spheres or whatever. Right. So, but the issue is you want to be having these levels of details of clusters, right? And you need to sort of go down, color in a whole. You need to sort of apply all the edits to a whole cluster, right? And all of the siblings before you can simplify your parent. So I think it's quite an easy algorithm to work out. The basic idea is you go down the tree, apply all of the edits to this thing, and you'll be like, so if we paint it down at L0, because we have brushes that paint specific levels of detail, that's how we get the size information. The size is right. So it's not 2x2x2 anymore, it's like 4x4x4 or 8x8x8, something like that. And you'll paint down in that area. But then for all the ones that don't target your LOD and target the next LOD, or the ones after it, you will make an array where those affect that area. So this will be broken into an octree, right? And each one of these go off into their children. You'll then build another array where all the edits that affected this area get put into another array. Now I was thinking, how can you build such a thing? Surely you just have you're having like 4 arrays you're building at the same time, and each array could be, you have to like max allocate for these things. And the way that I'm thinking about doing it is we basically have a linked list of arrays. So we only allocate like 256 at a time when we're passing these edits down, or something like that. So if someone, imagine there's a 256 cubed volume, which there isn't anymore. If someone puts a lot of edits down in this corner, right? Okay. say that's like 20 edits we've just made there. The first level up tree will be here, right? These guys won't even have any edits when we go, like, or whatever, so we won't even bother trying to process anything down here. This octree, you know, this one actually has one edit that kind of goes in. So this one will have like 1, this will have like 7, this will have like 8 or whatever, I don't know, this will have like 0 edits that get made for it. And you just, wait, if this was, I said like 20, but anyway, whatever. And actually I forgot to do a step for this whole thing. We would have passed like the 20 into here and made an array for that. So you're just making loads of these little arrays. And we'll probably, I think you're going to have thousands of edits. So maybe like 30, a linked list with 32 edits in an array, and you sort of just linked list them, right? So that means as you go down the tree, we can recurse down the tree, and when you've finished applying the edits to this node, you then pop on the children which have got edits, and you repeat the process again until you reach a cluster which is a leaf and doesn't have anything. Then this one will refine. It will look at, well, wait, what would it do? This one, you can guarantee that its parent is finished at this point. So what you say is you go, okay, how many spheres do I have? Do I have a 2x2? All right, this is gonna be a 4x4x4 or an 8x8x8. But you should be able to say, hey, this thing is, so this thing has a 2x2x2. Here's a good way of saying it. And imagine this sphere here, this bigger sphere here which covers them, is actually this guy and this LOD. You'll be saying, oh, it has a 2x2x2 in this quadrant, so fill in that sphere in the parent, basically. Yeah, fill in that sphere in the parent, and let's have a 2x2x2 here. And if these all exist, fill in that one. And then when all of these have been, when all of the children have come, bear in mind there should be 2 more spheres here that come from this guy or whatever. But anyway, I'm going up. But when all the children have came up here and reported back and saying, hey, I'm finished, then this one can repeat the same thing and go up to its parent. But it can't obviously because it's all 0. But, you know, that's the process basically. And we should be able to do that in a multi-threaded way and do a build and refine in a single step. Unlike our old solution, which required like 5 shaders and an occupation map, which is pretty cool. Pretty cool how I learned how we could reduce like 8 samples down to 2 samples or something dumb like that. And anyway, that was really cool what we made, but this solution I think will be far simpler. So I think it's just a 1 pass. I think it's a 1 pass system. There's a 1 pass shade. It's just a 1 shader, and it builds the whole thing, which is pretty cool. So basically, I'll just describe what I described again, but in text form. So we'll recursively apply recurse whatever, okay. Recursively apply the volume edits to each cluster. Okay, that's not a good way to say it. So you want to say apply all the edits to the root cluster, L0. So you say like, paint, yeah, apply all the edits to the root cluster. For the edits that apply to the current cluster, LOD 0. What sort of edits are you limited to if you want high performing? So currently we're just going to do ellipsoids and cuboids. So you basically have brush, an ellipsoid brush and a cuboid brush. You can do more shapes, but and you can also do like if you take a look at Dreams, when they did it, they had like Bezier curves and stuff, right? Where you can like do a Bezier curve and fill that in, and that'll be filled in with spheres, which is really useful when you want to build certain things, right? And that thing is kind of, you can do it, but another way you could probably do it is comprise that of spheres and just do tons of spheres edits, right? So you could just break it down into smaller edits, because you can basically step over this curve and just apply the rate, So we can do more complicated things and just compile them to, smaller operations and stuff. But for now, it'll just be those two shapes, because at the end of the day, it's like a paintbrush. But the more switch statements you have, the worse it would be, right? Apply all the edits to the current cluster, to the spheres in the current cluster. Here's a better way of saying it. For each edit in the current cluster. That's a good way of saying it. If edit target LOD is equal to cluster.lod, then sort of apply to the spheres, the affected spheres, right? If edit.target LOD is greater than cluster.lod, then make array, then append to array of edits for the child octree nodes that are affected, right? That's proper cool. And another little thing I want to add to that again is arrays are linked list chunks of maybe 32 or 256 edits to be decided, right? So that'll be of maybe to be decided, right? So that means we can, you know, this sort of solves the problem of growing, of sort of multiple growing arrays, and we don't know the final size. So that's a really clever trick. Right, so that's basically the gist of, so you're going down the tree and applying those edits and building more little arrays. I haven't crunched any numbers to see if this, of appending, like making these arrays of sub edits or whatever, if that is, they should be fine. Like these, I'm thinking the whole volume is going to take kilobytes of memory. So if we're repeating that maybe, you know, even if we repeat that 1,000 times, that's megabytes of memory. So it should be okay, but we shouldn't be repeating it thousands of times. Right, we'll be repeating portions of it thousands of times. So hopefully it's okay. Someone could probably bugger it up though. I don't know. We'll see. Anyway. So, and then you want to say recursively apply this to all child octree nodes that have, recursively applies to all child octree nodes that have edits, right? Amazing. So then, and then after you've, then what you want to say is, if, all right, if, okay, for each edit in the current cluster, so after we've processed all the edits, if no children, no child octree nodes okay, if any octree nodes have edits, recursively apply this to all child node. Recursively continue to all octree nodes that have edits. Now there's sort of like an else here, and the else would be basically construct a lower. Now this is where you get to save memory again. Yeah, this is where you'll get to save memory. So this would be saying like you've got take the 2 by 2 by 2 oh, that's way of saying it. Take each 2 by 2 set of spheres and downsample that to the parent cluster. If we are the last child, sort of downsample to the parent, then traverse up to the parent. And repeat. Yeah, that's pretty cool. So I think the main thing is that what happens then if you just recurse down the tree. You've allocated tons of spheres, allocated tons of clusters. You need to. How do you get rid of the clusters again? Yes, the only downside to this is we used to have the neighboring. We used to look at the neighboring. If your cluster was completely surrounded by other clusters, if your cluster is completely surrounded by other clusters, then it can possibly be removed. That's something we've got to think about. So let's put a pin in that today. To do, think about. So it might still have to be a 2-pass system, maybe. I'm not sure. Or maybe we could. But you can definitely stop at an LOD with this. You could stop at a specific LOD. Like you can load in the first so many LODs, simplify, and then carry on. Maybe. There might be a way. Gotta think about it. But yeah, do you think about how we can simplify and save memory while we build and make this possible, make it actually possible. Maybe we do need a multi-pass system like we had, but it should be possible. Yeah, it should be possible to achieve though. So it might be multiple shaders, but maybe we could do it in one pass still. Just got to think about how we're going to do it. Because we can do this recursive descent thing. We just got to have like a ring buffer or something like that. It's possible. But it's just a question of maybe you get so far and you've allocated everything. So now you need to look at the leaf nodes and sort of simplify and then continue. Maybe. Just got to think about how we're going to do that. But yes, that's what we're doing next stream. Is finishing off this plan. And then we'll probably execute on it. Bearing in mind, before I go on holiday, we've got 2 more streams, maybe Sunday and Tuesday. So we might just start doing this next stream and the stream after. But yeah. And then I'll be off for the whole of February. And then I'll be back in March. So if you guys want to keep posted on like, when's the stream back and all that, I'll be posting in the Discord as I usually do. So you can come by there and follow there. Wish I could study that history. Oh, how did the field of computing take off? Wish I could study that history. Yeah, not necessarily sure myself to be fair, but yeah, it goes back to like the 60s, doesn't it? Or maybe earlier than that. And it just slowly progressed from there. But it's pretty insane how fast computers are now compared to then. They started from like punch cards and stuff, right? Or even before that. But yeah, there's a you know like even before that they had like kind of like an analog computer, and not necessarily maybe I don't know. Yeah. Right. Yeah, I'm sure there's tons of little you know things for that. Um, like I'm sure there's tons of like history shows that have gone over that. Yeah, so after the holiday, so I've got two more streams until I go on holiday. After the holiday, I'll probably be back on Sunday, the 3rd of March time, because, I'll be back. Actually, no. When am I landing? No, I'll be landing here, so I won't be back until probably the Tuesday. That's when, because I go back to work this week. So, yeah, two more streams left, and then I'll be away for a whole of February, be back sort of this sort of time. And then I guess the whole of March is when we'll be getting the system up and running. It's going to be incredible. Yeah, definitely. It's going to be scattered everywhere. Oh, Kanji is actually screen sharing rather than just showing his back. Who's Kanji raid? It's really weird. The past 6 months, Kanji's just been showing his back and has been programming on a computer and just having the screens glaring. And I don't know why he was streaming that, but okay, hopefully his back's doing some form of programming and showing it. I see Godot, or Godot as people want to pronounce it. But anyway, no worries. Thank you so much for coming. Shinen, Shin, Shinigemi. Thank you for coming, guys. Thank you, Cranston. Appreciate it. Yeah, I hope you catch them too, man. Missed you, man. Good help. You've been a good help. Right. Yeah. Have a good start to your weekend. I'll see you on Sunday. I forget what day it is. Right. Catch you later. Bye.